So now let's start with the another important topic in GATE examination for thermodynamics point of view, that is IC engine. So now we will talk about IC engine. IC engine. So first we will see the fundamentals regarding IC engines, and then we will solve some of the problems based on IC engines. So first let's define the IC engine. So for IC engine, I am starting with the heat engine, and then I will describe what is the meaning of IC engine. So heat engine. First of all, I am taking heat engine. So heat engine is a device. A heat engine. A heat engine is a device. Is a device which transfers the chemical energy. Which transfers the chemical energy of a of a fuel into thermal energy into thermal energy and uses its energy and uses its energy to produce mechanical work to produce mechanical work. So this one is a general definition of heat engine. Means the heat engine is a device which is converting low grade energy into high grade energy. Low grade energy means the heat energy, which is converted into high grade energy into means mechanical work. So basically the heat engines we are having classified into two categories. So heat engine I will classify into two categories. One is external combustion engine, and second one is internal combustion engine. So by name itself we can say that in external combustion engine the combustion will takes place outside the combustion chamber, but in case of internal combustion engine the combustion will takes place inside the combustion chamber. So this is the main difference between the external combustion engine and internal combustion engine. So I will write combustion takes place outside the cylinder. You can say that outside the cylinder. Here in case of internal combustion engine, combustion takes place inside the cylinder. So that's why we are calling it as an internal combustion engine, because combustion takes place inside the cylinder. So now I will give some of the terminology related to IC engine, because we have to concentrate only on IC engine. So now I am giving some terminologies. So I will write engine terminology. So we will discuss about engine terminology. First one is piston swept volume. Piston swept volume, which is denoted by Vs. So remember one thing, whenever in the problem some volume is mentioned without saying it is piston swept volume or total volume, so by default it will be piston swept volume. So the nominal volume generated by the piston when traveling from one dead center to the another dead center, that is called piston swept volume. So I can write the nominal the nominal volume generated by the piston when when traveling from one end when traveling from one end means one dead center to the next one. So during this interval, the volume generated is called swift volume. So Vs is nothing but A into L. So here A is the area of cross section of piston and L is the length of stroke. So I can write A is area of cross section piston, L is length of stroke. Now let's talk about clearance volume. So now clearance volume, that is the nominal volume of space on the combustion side of the piston at the top dead center. Means uh, it's a clearance between the piston top and the cylinder when it is at the top dead center or when it is at the extreme dead center. So I will write the clearance volume, that is denoted by Vc. The nominal volume of the space on the combustion side of the piston at top dead center. I will again repeat, the nominal volume of the space on the combustion side of the piston at top dead center is called clearance volume. So now let's talk about cylinder volume. So cylinder volume is nothing but the sum of swift volume and clearance volume. So cylinder volume is denoted by V. So it is nothing but the sum of piston swept volume and clearance volume. So I can write V equals to Vc plus Vs, that is the cylinder volume, or we can say the total volume. Now let's talk about compression ratio. So now we'll talk about compression ratio, which is very important in IC engine. It is denoted by R. It is the ratio of cylinder volume to the clearance volume. It is the ratio of cylinder volume to clearance volume. So mathematically we can write R equals to V by Vc. It's a ratio of cylinder volume to the clearance volume. Now let's talk about performance parameters. These parameters are very important from that point of view. So we will more concentrate on performance parameter. So performance parameters. So now let's talk about the performance parameters. So first I am taking indicated power. So I am taking first indicated power, that is denoted by IP. So first I will talk about indicated power. That is the power developed inside the cylinder of the engine is called indicated power. So I can write the developed power developed inside the cylinder of the engine is called indicated power. Is called indicated power. I will again repeat. The power developed inside the cylinder of the engine is called indicated power. And indicated power we can write PMAL, then K into N divided by 60 is in kilowatt. So here I will tell what is the meaning of PM. A and L we have already discussed, that is area of cross section of piston. L is the length of stroke. And now we have to define PM, K and N. So here PM is mean indicated pressure. So PM is mean indicated pressure. Mean indicated pressure means that is the pressure, average pressure inside the cylinder, that is mean indicated pressure. So PM is mean indicated pressure in kilopascal, and K is N, that is N RPM in case of two-stroke engine. In case of two-stroke engine. So now I will define what is the meaning of two-stroke engine. So in IC engine we can also classify the engine on the basis of number of revolutions. So in two-stroke engine the whole cycle will complete in one revolution. So that is called two-stroke engine. Similarly, K will be N by 2 RPM in case of four-stroke engine. Four-stroke engine. So four-stroke engine, similarly, if the engine cycle is completed in two revolution of the crankshaft, so that is called four-stroke engine. So now we are having two strokes and four strokes. So remember one thing, in case of two-stroke engine you have to put K equals to N, and in case of four-stroke engine you have to put K equals to N by 2, where N is RPM and small m is nothing but number of cylinders. So by this way we can easily calculate the indicated power. So now let's talk about brake power. Brake power, that is denoted by BP. So we have already discussed one power is called indicated power, that is generated inside the cylinder. But the actual power we are getting at the crankshaft is useful for our work. So we can say that the power available at crankshaft is called brake power. So now it's clear, whenever in the problem they mention some power without saying it is indicated or brake power, so by default it will be brake power because this power is available at the crankshaft. So brake power we can easily calculate with the help of this formula, 2 pi Nt by 60. So here N is the number of revolution per minute and T is the torque. So by this way we can calculate BP. So now I will give the relationship between IP and BP. So third, IP equals to BP plus FP. So here FP is nothing but frictional power. Frictional power means the power which is developed inside the cylinder. If it is going up to the crankshaft, then there will be some frictional loss. So we can write IP equals to BP plus FP. FP means sum of the power will waste in overcoming friction. Now let's talk about mechanical efficiency. So now we will discuss about mechanical efficiency, that is denoted by eta mech. So mathematically it will be equals to BP by IP. BP by IP. Now I will talk about some more efficiency. So let's take indicated thermal efficiency. Indicated thermal efficiency, that is denoted by eta IT. So indicated thermal efficiency is nothing but the ratio of energy in indicated power to the fuel energy. So I will write, that is energy associated with IP divided by fuel energy. Fuel energy. So indicated thermal efficiency, I can write IP divided by MF into MF into calorific value. Calorific value. So by this way we can find out the indicated thermal efficiency. IPMF is mass of the fuel and CV is calorific value. Similarly, we can also define brake thermal efficiency. So now we will define brake thermal efficiency. Brake thermal efficiency. So brake thermal efficiency is denoted by eta BT, and again it is based on brake power. So similarly we can write the formula for that. Eta BT is nothing but energy associated with BP, that is brake power, divided by fuel energy. Divided by fuel energy. So mathematically I can write BP divided by MF into CV. Here MF is mass of the fuel and CV is calorific value. Now let's take volumetric efficiency. So now we will discuss about volumetric efficiency. Volumetric efficiency, that is denoted by eta V. It is defined as the ratio of the air actually induced at ambient condition to the swept volume of engine. So I will write it is defined as the ratio of air actually induced at ambient condition, ambient condition to the swept volume of the engine, to the swept volume of the engine. So I will again repeat, the volumetric efficiency is nothing but the ratio of actually induced, the air actually induced at the ambient conditions to the swept volume of the engine. So I will write in mathematical form, that is actually induced air. So actual volume of air divided by swept volume. Swept volume. This one is a typical definition for the volumetric efficiency. Now I will define one more term, that is relative efficiency or efficiency ratio. Relative efficiency or efficiency ratio. Efficiency ratio. So the relative efficiency or efficiency ratio is nothing but ratio of thermal efficiency of the actual cycle to that of ideal cycle. So now remember one thing, we will discuss in later, the air standard cycles for the IC engines are Otto cycle, diesel cycle and dual cycle, and these cycles are ideal cycle. But in reality the cycle will be different, because in ideal cycle we are assuming only the air as a working substance and the specific heat is not changing, but in reality the working substance is mixture of air and fuel, and the specific heat is also varying during the course. So these are some of the assumptions we are making for ideal cycle, but in reality it will be different. So that's why we are taking the ratio for thermal efficiency of actual cycle to the ideal cycle in terms of relative efficiency. So now first I will write what is the relative or efficiency ratio. It is defined as, it is defined as the ratio of thermal efficiency of thermal efficiency of actual cycle to that of ideal cycle. So we are comparing the actual cycle thermal efficiency with ideal cycle thermal efficiency. So I can write relative is actual thermal efficiency divided by air standard efficiency. Air standard efficiency. Now let's talk about specific fuel consumption. So now we will talk specific fuel consumption, that is SFC. It is generally expressed in kilogram per kilowatt hour. So now on the basis of brake power and indicated power, we are having brake specific fuel consumption, that is mass of the fuel divided by BP. It will be in kilogram per kilowatt hour. On the basis of indicated power, ISFC, indicated specific fuel consumption, again MF by IP, it will be in kilogram per kilowatt hour. So now let's take another important parameter, fuel air ratio. Fuel air ratio. It is the relative proportion of, it is relative proportion of the fuel and air in the engine. Fuel and air in the engine. It's a relative proportion of fuel and air in the engine. So fuel air ratio is nothing but mass of fuel divided by mass of air. Now let's take another parameter, that is mean piston speed. Mean piston speed, that is given by 2ln. That is very important. Here L is length of cylinder, sorry, that is length of the stroke, we will say the length of the stroke here, and N is RPM, rotation per minute. So this one is the mean piston speed. Now let's talk about another important parameter, equivalent ratio. Equivalent ratio. So equivalent ratio is denoted by phi. So phi is actual fuel air ratio to the stoichiometric fuel air ratio. Fuel air ratio means the fuel air ratio during the operation of the engine will change. It depends on our application. Like for starting, cold starting or idling, we are having the high fuel air ratio. But for economy zone or when the speed is maintained, then we are having the chemically correct fuel air ratio. And during the more power and during the more power generation, we are required more fuel air ratio. So on the basis of that, we are defining the equivalence ratio. So I will define phi equals to 1 for chemically correct, for chemically correct fuel air ratio. Phi is less than 1, that is lean mixture. Lean mixture means fuel is less. Phi is greater than 1, that is rich mixture. Rich mixture means fuel is more. So according to our requirement, we are supplying more fuel, we are supplying less fuel, or we are supplying chemically correct fuel. We will discuss about air standard cycles. Now we will discuss about air standard cycles. So first I will write the assumptions in ideal or air standard cycle. These are very important so that we can understand what is the different things in actual cycles. So assumptions in ideal or air standard cycle. Air standard cycle. Now I will write the assumptions in ideal or air standard cycle. So first assumption, the working medium is a perfect gas. The working medium is a perfect gas. Perfect gas. That is, it follows the law. It follows the law PV equals to mRT. But in a real cycle, that is in actual cycle, working medium is a real gas. So that is the difference between air standard cycle and actual cycle. Second assumption regarding air standard cycle, working medium has constant specific heat. The working medium has has constant specific heats. The working medium has constant specific heat, but in actual cycle the working medium is having variable specific heat, means the specific heat is changing during the course. Third assumption regarding air standard cycle, the working medium does not undergo any chemical change. The medium working medium does not undergo any chemical change any chemical change throughout the cycle. But in actual cycles the working medium chemical composition will change throughout the cycle. The assumption number 4, the operation of the engine is frictionless, means we are considering all processes are reversible. All processes are reversible, but in reality the all processes will be irreversible. So these are the basic assumptions made in air standard cycles. So now one by one I will take the air standard cycles for IC engine. So first I am taking Otto cycle. So Otto cycle, that is a very common type of internal combustion cycle used in spark ignition engines. So I will write, it is a very common type of cycle used in spark ignition engine, spark ignition, or we can say that petrol engine, spark ignition, petrol engine. So that is Otto cycle. So now first of all I will draw the PV diagram for this cycle, and then we will discuss about the efficiency of this cycle. So for Otto cycle I am now drawing the PV diagram. So here I am drawing the PV diagram. So here I am not considering the suction and the exhaust. I am just starting with the compression. So that is our 1 to 2, 1 to 2, 2 to 3 is constant volume heat addition, that is 2 to 3, 3 to 4 is again adiabatic expansion, and 4 to 1, that is a when the exhaust valve is open, that is blow down, or we can say that it's a blow down process, right? So 4 to 1. So this one is the typical diagram for the Otto cycle on PV basis. So here I will write, here we are supplying Q1, here Q2 is rejected, here compression work, here expansion work. If you see these processes, so here entropy is constant, that is reversible adiabatic, and we can also say that PV to the power gamma was to C for these two processes. So this one is the representation of Otto cycle on PV diagram. Similarly, I can represent the Otto cycle on TS diagram also. So on TS diagram, the representation will be like that: 1 to 2 isentropic compression, 2 to 3 constant pressure heat, 2 to 3 is constant volume heat addition, 2 to 3, 3 to 4 again isentropic expansion, 4 to 1, that is constant volume heat rejection. So this one is a representation of process on TS diagram. So now I will directly write the formula for efficiency of Otto cycle. It will be 1 minus 1 upon Rk to the power gamma minus 1, where Rk is compression ratio. Compression ratio. So this one for the Otto cycle efficiency is directly calculated by this formula. I am again repeating 1 minus 1 upon Rk to the power gamma minus 1. The Rk is the compression ratio. So again I will define the compression ratio. It is volume at the beginning of compression. Volume at the beginning of compression. Beginning of compression divided by volume at the end of compression. Volume at the end of compression. So here from diagram, if you see volume at the beginning of compression, here it's V1. At the end of compression it's V2. So I can write V1 by V. Now from previous discussion I can write the efficiency of air standard Otto cycle is a function of compression ratio. So I can write the efficiency of the air standard Otto cycle is a function of compression ratio only. Compression ratio only means higher the compression ratio, higher will be the efficiency. The higher the compression ratio, the higher will be efficiency. The higher will be efficiency. So higher the compression ratio, higher will be the efficiency. But we can't go beyond a certain compression ratio. So because it will increase the noise and the knocking phenomena will happen. So I can write the compression ratio cannot be increased beyond a certain limit. The compression ratio cannot be increased beyond a certain limit because of a noisy and destructive combustion phenomena. Because of a noisy and destructive because of a noisy and destructive combustion phenomena. That is known as detonation. If we increase the compression ratio, the chances of detonation will be increased. It also depends on fuel, the engine design and operating condition. It also depends upon the fuel, the engine design and the operating condition So the choosing of compression ratio in spark ignition engine or engine which is based on Otto cycle is very important. So it also depends on the fuel, engine design and operating condition. Now let's talk about diesel cycle. So we have already seen like in Otto cycle, the efficiency is depending on compression ratio, but there is some limitation on the compression ratio. But in diesel cycle, we are compressing the air alone and then we are injecting the fuel into the cylinder. So that is a difference between the spark ignition and compression ignition engine. Because in spark ignition engine, we are supplying the fuel mixture, that is fuel air mixture, into the cylinder, and we are compressing the fuel air mixture in the cylinder, and then we are giving a spark for the combustion. But in diesel cycle, what we are doing, we are compressing the air alone, and after compression we are injecting the fuel, and by this way we are getting the combustion. So that is a basic difference between spark ignition and compression ignition. So the diesel cycle, so the diesel cycle is basic cycle for compression ignition, that is called CI engine. So the diesel cycle is the basic cycle for the compression ignition engine. So first I will draw the PV and then TS diagram, and we will see the formula for efficiency. That is pressure. Here we are having volume. So now 1 to 2, that is isentropic compression. 2 to 3, that is constant pressure heat addition. Remember one thing, in Otto cycle there is a constant volume heat addition, but in diesel cycle there is a constant pressure heat addition. And 3 to 4, again there is a isentropic expansion, and 4 to 1 is heat rejection. So now this one is compression, this one is heat addition, this one is expansion, this one is heat rejection. So similarly here we are S equals to C, S equals to C, and here we are having PV to the power gamma equals to constant. Similarly here having PV to the power gamma equals to constant. So that is a typical representation of a diesel cycle on PV diagram. So now I will consider the same cycle on TS diagram. So these are the constant pressure curves. Again you have to start 1 to 2 isentropic compression, 2 to 3 constant pressure heat addition, that is 2 to 3, that is constant pressure heat addition, 2 to 2, 3 to 4 again isentropic expansion, and 4 to 1 heat rejection. So this one is a typical representation of diesel cycle on TS diagram. And now let's calculate the efficiency of diesel. So efficiency of diesel, we are having the formula for that. I am directly writing this formula for diesel cycle. We are having 1 minus 1 upon gamma 1 upon Rk to the power gamma minus 1 into Rc to the power gamma minus 1 divided by Rc minus 1. So this one is a formula for efficiency diesel cycle. That is 1 minus 1 upon gamma into 1 by Rk to the power gamma minus 1 into Rc to the power gamma minus 1 by Rc minus 1. So we have already know this thing. We are having compression ratio, that is already discussed, Rk, and we are having one more thing here, that is Rc. So now I will discuss about Rc. So Rc is nothing but cut off ratio. Cut off ratio. Rc is nothing but cut off ratio. So cut off ratio I am defining here, that is V3 by V2. If you see this process here, so we are supplying a fuel in the process 2 to 3. So we are starting at 2 and we are ending at 3. So it's the ratio of V3 by V2. So remember, the cutoff ratio is nothing but the ratio V3 by V2. So if we plug RC here, RK here, then we can easily find out the diesel cycle efficiency. Now let's take a limited pressure cycle. We can also call mixed cycle or dual cycle. So now take limited pressure cycle, mixed cycle, mixed cycle, or we can say that. So that is for high speed engine, high speed engines. We are generally talking for dual cycle. So first I will draw the PV diagram for that. So PV diagram for dual cycle. So 1 to 2, same thing, isentropic compression. 2 to 3, constant volume heat addition. 3 to 4, also constant pressure heat addition. 4 to 5, again isentropic expansion. 5 to 1, that is constant volume heat rejection. So I am now showing the process. Is 5 1. Here WC, that is S equals to C here. Here we are having heat addition Q1. Here also we are having heat addition Q1. Here again S equals to C. That is expansion work and heat rejection Q2. So this one is a typical representation of dual cycle on PV diagram. So now I can represent this thing on TS diagram also. TS diagram. So here I am representing these things on TS diagram. So from 1 to 2 we are having isentropic compression. 2 to 3 we are having Q1, that is constant volume heat addition. 3 to 4 again we are having heat addition but at constant pressure, and 4 to 5 again I am having isentropic expansion, and 5 to 1, that is constant volume heat rejection. So this one is a typical representation for dual cycle on TS diagram. So now consider the efficiency of dual cycle. So but before going into efficiency of dual cycle, let's take one more parameter, that is constant volume pressure ratio. So because we know compression ratio, I will again define all these things here. Compression ratio, that is nothing but RK, that is V1 by V2, we have already discussed. Similarly, cutoff ratio we have already defined, denoted by RC. So cutoff ratio here it will be V4 by V3 according to diagram. So V4 by V3, and now we are having constant volume pressure ratio, that is RP. So here constant volume pressure ratio, if you see for this process, so we are having P3 by P2. So these are the terms related to the dual cycle, and now we can easily find out the efficiency of dual cycle. So 1 minus 1 upon Rk to the power gamma minus 1 into Rp into Rc gamma minus 1 divided by Rp minus 1 plus gamma Rp Rc minus 1. So this one is the formula related to 12 cycle. I will again repeat: 1 minus 1 upon Rk to the power gamma minus 1 Rp into Rc to the power gamma minus 1 divided by Rp minus 1 plus gamma Rp Rc minus 1. Now I will discuss the important comparison between Otto, diesel and dual cycle. So the comparison of Otto, diesel and dual cycle. Now I will show the comparison of Otto, diesel and dual cycle. So first, for same compression ratio, for same compression ratio and heat rejection. For the same compression ratio and heat rejection, we can say efficiency of Otto is greater than efficiency of dual is greater than efficiency of diesel. So remember this thing. This thing is very very important. And we can say for same compression ratio and heat rejection, the efficiency of Otto is greater than efficiency of dual is greater than efficiency of diesel. Similarly, for same maximum pressure and temperature, for same maximum pressure and temperature and heat rejection and heat rejection, we can write efficiency of diesel is greater than efficiency of dual is greater than efficiency of Otto. So these two comparison on the basis of same compression ratio and on the basis of same maximum pressure and temperature are very important. So remember this thing. So sometimes they can directly ask in the GATE examination.